Okay, right. So another day of new topic for today. Let me just remind you real quick of the last couple topics that we covered. We spent a bunch of time in section 5.3, and that was about representing linear transformations with matrices. But really kind of more what it was about is how bases are the things that do that. Right? A basis is a way that you can represent a linear transformation as a matrix. And we talked about how then do you do a change of basis and stuff like that. So roughly speaking, 5.3 is about change of basis, bases and change of bases. Then we had a seemingly new topic last time, which was eigenvectors and eigenvalues. I mean, it was unrelated, right? Totally different thing. There's an equation, and then there's a whole process for finding them and a couple of related matters. And I said seemingly unrelated because, in fact, there's a strong relationship. Change of basis 5.3 stuff and eigenvector 5.4 stuff. If you kind of, in a certain sense, bring them together, that we'll see develop over the course of today's talk. Something remarkable and very interesting and ultimately very powerful happens. So anyway, that's the quick preview. So kind of be on the lookout for that as we go along through here. So starting off with a definition of something called similarity. Two matrices, and by the way, this is just a definition, right? We'll talk about the choice of terminology in a minute. But we're going to use for the moment the word similarity. Two matrices are similar if there's some invertible matrix P, and if you can do this little construction here called a conjugation. If you can conjugate A to result in B, then we say that A and B are similar. Okay, so what an odd choice of term, right? Similarity seems to suggest that A and B should have something in common. Well, what in the world do they have in common? Right? Okay. Right. Exactly. Before I answer that question, real quick, another terminological thing. These two matrices that are similar are called conjugates of each other because, from a semantics point of view, one is achieved from the other by conjugating. So it's just terminology. Okay, so again, what do these two matrices A and B have in common, thus motivating the term similarity? Well, quick reminder. This structure of an equation, we've seen a structure that looks a lot like that before. That's this equation, right? So now again, flash back to 5.3. You can start to see hints of a 5.3 connection. This is the formula that we had for how to do a change of basis on a linear transformation. So specifically, if you have some linear transformation T, right, and if you know how to represent the linear transformation with respect to the script V basis, if you want to know how to write the linear transformation with respect to the script V prime basis, right, well, the way you do that is by this little formula, which you notice is a conjugation, right? It has got that same structure. The matrix on the left here is exactly the inverse of the matrix on the right. Roughly speaking, you have to switch from V prime to V language, and then from V back to V prime language. So inverses. Okay. It turns out that anytime this happens, in effect, this is happening. Right? Why is that true? Why is it that anytime these happen? Well, all I need is I need to know that for every invertible matrix, in other words, anytime such an equation up there happens, well, it happens because there's a P matrix, something that's invertible. I just need to know that every invertible matrix can be thought of as a change of basis matrix. If that's true, then everything falls into place. And it's a exercise that I'm going to leave for y'all to show. Every invertible matrix P is a change of basis matrix. Here's the theorem. Here's the proof. Well, here's the outline of the proof. the details of the proof. How would you write down, for example, hypothetically on an exam, if this was an exam question, how would you write this proof? I'm going to leave as a practice exercise for y'all. The big idea is right here. The big idea is that if you have an invertible matrix, you want to show that there exists a basis V that makes this a change of basis matrix. Well, the columns of P are that basis. So that's the trick. And now it's all you'll have to do is to confirm that with that choice, P actually is, as required, a change of basis matrix. Okay, so details for y'all to confirm. So going back up here, knowing now that every invertible matrix is indeed a change of basis matrix, every time you have a similarity, you're really doing a change of basis on a linear transformation. This tells us what it is that A and B have in common. Again, the term similarity suggests that there's a shared feature or a shared something. That shared feature is whatever the underlying linear transformation is that those matrices represent. Right? So if B and A are similar, if they are conjugates of each other, they represent the same linear transformation. They're just representing that same linear transformation with respect to different bases. So, yeah. Okay. All right. So, interesting. Now, this is going to allow us to define the next term of interest, and the term is diagonalizable. You'll recognize this from the title of the section. Why we care about diagonalizability? Well, we're not gonna get to that today, I'm afraid. I'll be able to make some very vague references about that. But the real payoff of diagonalizability is this is a huge concept. And ultimately, in Chapter 6, we're going to see that we're going to solve differential equations with this idea of diagonalizability. So, again, foreshadowing. Keep your eyes open for that. So the definition, and I'm going with the book's choice of definition on this. Matrix is diagonalizable if it is similar to a diagonal matrix. I want to talk about the lingo now a little bit. Keep in mind that similar, well, let's see, do it like this. Similar means by way of a conjugation. Right? So think about it from that point of view. A matrix is diagonalizable if there's something you can do to it, namely a conjugation. That's what similarity is. If by doing a particular thing, you make it diagonal. So the able at the end of diagonalizable means by conjugation. And so diagonalizable because you're making it into a diagonal matrix. Okay. All right. So, why we would care about this concept, again, that will come later. All right, now let me give you a different point of view on diagonalizability. By the way, this next point of view on diagonalizability is not discussed much, if at all, if I recall, in the book, but I think this is really valuable. This is the way I think about diagonalizability. It's much more intuitively satisfying for me. It goes to interpreting this word similarity that we talked about on the previous page. So let me remind you, similarity. Yeah. Similarity means one is a conjugate of the other. But it also means, as we saw on the previous page, that the two matrices ultimately represent the same linear transformation, just with respect to different bases. Or, as I also like to say, the two matrices represent the same linear transformation, just in different languages. Right? So let's take that notion of similarity, all right, and let's then reinterpret this definition of diagonalizability that we have here. So a matrix is diagonalizable if it's similar to a diagonal matrix. Okay, well, similar means that by change of basis, preserving that underlying linear transformation, we can take the original matrix A and turn it into a diagonal matrix that I didn't give a name to. Maybe we call it D, something like that. All right, let me take a pause here for a second. Does anybody have any questions? By the way, let me recognize, I know I'm throwing a lot of ideas at you all at the same time here, right? So there's this definition of similarity. There's then a different point of view on similarity, digesting this idea that you can think of conjugations as a change of basis, and then applying that concept of change of basis being the same as a conjugation to make this interpretation of this new definition of diagonalizability. It's a lot to digest all at once. So pause. Questions? Anybody? Take the time, by the way. I mean, after the lecture's over, I know in some, you may not be to the point where you have a question formed yet, and that's totally fine. I think it's a really good idea to take the time after the lecture's over to, identify what maybe are you having a little trouble chewing, right? You can go back and listen to that portion of the lecture again in case that might help. Sometimes multiple passes through can make a big difference. Okay. So we had this idea of similarity, different points of view on similarity. We're talking about, by that process, turning a matrix into a diagonal matrix. All right. Why a diagonal matrix? What's so great about diagonal matrices anyway? There's some big reasons that we like diagonal matrices. The big one is going to come in chapter 6. It's going to turn out that a certain kind of differential equation is really, really easy to solve when a certain matrix associated with that differential equation is diagonal. So there's going to be a big punchline there. But for the moment, let me just show you one quick nice thing about diagonal matrices. Diagonal matrices have this wonderful feature that the eigenvalues and eigenvectors are obvious. And just as a for example, before I point to the theorem, let's see what is a eigenvalue and an eigenvector for this matrix that you'll notice is diagonal. Can I think of some vector that I can multiply by here, and magically I get a scalar times that same vector? And here's, the free obvious answer, obvious once you see it, that is. E1. Multiply E1 there. What do you get? You get 3, 0, 0, which is a multiple of E1, right? And specifically, the multiple is 3. Right? Notice it is a diagonal entry. That is the eigenvalue, and it is the what I'll call corresponding. Oh, let me do this in blue. The corresponding standard basis vector. That is the eigenvector. So standard basis vectors are eigenvectors. Diagonal entries are the eigenvalues. Now I'm going to leave it as an arithmetic exercise for y'all to notice what the other two eigenvectors are and what their eigenvalues are. And let me just tell you so E2 and E3 are also eigenvectors, and their eigenvalues are the next diagonal entries. And again, it's a matter of writing down the arithmetic and observing it. Yeah, sure enough, it works. So that having been observed here, here then is the theorem. And I'm not going to prove this again because it'd be sort of mostly notational clunkiness to be able to prove this. It's not. I just don't want the course to go there. But I think this is highly appealing. That diagonal entries have easy eigenvectors, namely always standard basis vectors. Easy eigenvalues, namely just those diagonal entries. A la this calculation here. All right. So, a bunch of abstract talk. We have a definition of similarity, definition of conjugation, point of view on that in terms of change of basis, another abstract definition, right? Let's see if we can kind of, oh gosh, I'm getting ahead of myself. Let me go ahead and do the example, numerical example. Okay, so here's a matrix A. By the way, we're going to do a lot with this matrix. You might even recognize this matrix. This is the same matrix for which we've already found the eigenvalues and the eigenvectors. We're going to keep using this matrix in multiple instances because we already know its eigenvectors and eigenvalues, and thus we save ourselves the inconvenience of having to every time go through and read, what are the eigenvalues of this matrix? What are the eigenvectors of that? I mean, y'all know how to do that. That's a process. We don't need to repeat that. So anyway, this matrix, we already know the eigenvalues and the eigenvectors. Okay. Let's see what happens if we do a change of basis using this basis. Namely, let's use the eigenvectors to form a basis. Weird, right? Okay, but I mean, go with me on this. Let's use the eigenvectors to form a basis, and then let's do a change of basis. Namely, let's conjugate, right? Change of basis is a conjugate. And see what this matrix is similar to if we use this new basis. Okay. There's two ways to come at this. First, I think is an easy first step is, again, I was given this matrix. We know that when we do a conjugation, we're just doing a change of basis. So I'm just going to try to find the matrix representing T with respect to now my new basis, script T. We have a formula for this, right? We take these basis vectors, we do the linear transformation to them, we write the outputs in that language. So the columns are those. That's from 5.3. Right, the way you represent a linear transformation in the language of a given basis. Those are the columns. And by the way, this is an easy calculation, as it turns out, at least in this case, because here's the thing: V1, that first basis vector, well, it's an eigenvector, so T of V1 is negative V1. How about that for lucky? How nice. Right? And now, next question, how do I write negative V1 as a linear combination of V1 and V2? Well, this is another one of those, it's staring you right in the face. Negative V1 is, well, negative 1 V1, and then plus nothing else, so plus 0 V2. So the coordinates of negative V1 with respect to script V are these numbers. So do it like that. Yeah. Okay. Analogously, what is T of V2? Well, T of V2 is 4V2 because V2 is an eigenvector. Right? What does this linear transformation do to V2? It does what the eigenvalue says. It multiplies it by 4. Right? And how do I write 4V2? As a linear combination of V1 and V2. Well, 4V2 is 0V1. Let's see if V1's in here, right? So 0V1 and then plus 4V2. That's second coefficient 4. Okay, so I've gone through the process here of, finding the columns. The columns are this. And those numbers turned out to be easily computed because because of these algebraic relations that come very conveniently from the fact that these are eigenvectors. And we can put those together then. Remember that these are the columns. So the first column is that. Second column is that. And here's my new matrix. So I have conjugated. I started with this A matrix. I did a conjugation, aka change of basis, to get the same linear transformation, just written in a different language. And lo and behold, it's diagonal. So this is not just a conjugation. This is a diagonalization of that original matrix. All right? Everybody on board so far? Now, was this just a lucky break? Right? I mean, I've showed that for this one matrix, it works out nicely that if you use the eigenvectors as your new basis, that stuff works out. And it turns out this is not a coincidence. It turns out that this, I'm going to loosely say, always works. I have to put an asterisk on that. But if you can come up with a basis consisting entirely of eigenvectors, this is going to work. And by the way, you can kind of see it happening. Why is this always going to work? How am I going to always get this to be diagonal? Well, one column at a time, this being diagonal, well, that happens because that entry is a 0. Why is that entry a 0? Well, it's because this entry is a 0. Well, why is that a 0? Well, it's because there's no V2s in here. And why are there no V2s in T of V1? Well, it's because V1 is an eigenvector. Right, so we just kind of trace it back through the process, and you can see this, you kind of expect anyway that this should always go down if you have a basis of eigenvectors. Okay. Now, let me show you the same calculation again from a kind of a different point of view. Remember, you can compute TVV, one column at a time. That's what we did here. Or you can compute it as a change of basis on linear transformations from the original matrix, which is in S language. In other words, as a conjugation. And in order to view it as a conjugation, well, okay, there's my original matrix in S language. What I'm going to conjugate it by is this change of basis matrix from V to S. I mean, that's what makes the Lego pieces fit together, right? The reason that this product of three matrices here is this is because, well, V input, this gives you an output in S language. Cool, this takes S language as its input. I can do the linear transformation starting in S language. My output comes in S language. Oh wait, I didn't want my output in S language, I want my output in V language. So we then convert from S to V. Right, so it's just, these just happen to fit together in such a way as to do exactly what this does. So that being the case, this change of basis matrix consists of this basis written in standard basis language. The script V basis, of course, the whole point was that it was eigenvectors. So rather than computing this by doing one column at a time, like we did up here. Here, let me, rather than doing this calculation to give me that matrix, I could instead do this calculation, and it'll give you the same thing. Okay. All right. So now it remains, I've got one numerical example under our belt. I think it's kind of plausible that you can kind of see how this sort of really should work whenever you have all eigenvectors. But we don't want just a plausibility argument. Let's go ahead and prove this. I'm going to show you two nice proofs of this fact. Here's the fact, by the way. A matrix is diagonalizable if and only if there is a basis for Rn consisting entirely of eigenvectors. This turns out to be a remarkably convenient little proof. There's not that much to it once you see it. It's a very clever argument, though. So let me get this whole page on at the same time. And notice that all this statement here says is that A is diagonalizable. Now, pause. I say A is diagonalizable. What it means to be diagonalizable is that the matrix is conjugate to a diagonal matrix. So this statement here just says A is diagonalizable. I'm claiming that this is true if and only if there exists a basis of Rn consisting entirely of eigenvectors. Well, this is what that would look like. Right? And how do you do a matrix multiplication? Looking down here at the bottom of the page, matrix multiplication, we take the left matrix and we multiply by the columns of the right matrix, one column at a time. So this matrix equation says A times V1 is a constant times V1. A times V2 is a constant times V2, etc. Right? And so as long as this matrix here is invertible, that makes those columns a basis. Old chapter 2 result. Right, so roughly what I need to do is just do the algebra to show that this green equation representing diagonalizability and this blue equation representing the assertion that there is a basis entirely consisting of eigenvectors, I just need to show that green implies blue. And likewise, that blue implies green. I just need to show algebra that allows you to get back and forth between the green and the blue. Yeah.
How come in the third step you didn't divide by the list of vectors, the matrix of vectors? Since I get both of those matrices were invertible.
So I'm not seeing, I'm sorry, what?
How come you didn't cancel out the two matrices of vectors?
Oh, you're talking about why didn't I cancel these?
Yeah, instead
Yeah. So very importantly, matrix multiplication is not commutative, right? So the problem is that this one here is on the left, this one over here is on the right. And so you just can't do it, right? Another minor point out while we're here, let me just point out cancellation's not really a thing, right? Cancellation is just a kind of a euphemism for divide. We can't divide matrices, right? So at best we can multiply by an inverse matrix, and actually that is the first step here. The first step of what to do is to we're going to multiply by here, let me label over here, by the way, for convenience. This matrix here, I'm just going to call it P for the moment. We're going to multiply by P on the left on both sides of the equation. And that gets us from the first step from the first line to the second line. Everybody good? Yeah. Okay. So that multiplication by P effectively puts this over to the other side of the equation, and then all that remains is to notice that if you multiply bad color choice, if you multiply these two matrices here, this is another chapter 1 reference, a matrix whose columns are V1 through Vn multiplied by a matrix whose diagonal entries are lambda 1 through lambda n. Linear combinations of these columns, using these columns as coefficients, just gives you this. So again, section 1.2, one of our interpretations of matrix multiplication. So, that's really all it is. The proof that this fact is true, the proof of this if and only if, is just this algebra showing that the way we write green in algebra is this equivalent to the way we write blue in algebra. Yep.
Can you explain how the blue means that there's the basis for it?
Yeah. So the blue equation, as I have it written here, just by itself, just means that these vectors V1 through Vn are eigenvectors. Right? See what I'm saying? Yeah, that's the again, interpreting matrix multiplication one column at a time. Right? So V1 through Vn are eigenvectors. Now that itself doesn't prove that there is a basis consisting of eigenvectors. It just proves that I found n eigenvectors. So I just need to know that they're independent, and so that's what I have circled in yellow here. I refer you back to the idea that if this matrix is invertible, then the columns are a basis. Right? So by assumption, P is invertible, therefore its columns are a basis, and vice versa. Okay, so this is one way to prove this result. Again, the punchline of this is, hey, if you have a basis consisting of eigenvectors, you can diagonalize. It's a fancy way of saying, yeah, this is always going to work. Just use your eigenvectors as your basis, and you can diagonalize with that basis. Okay, now I want to show you another proof of this same fact, and it seems silly. We've already proved it. Right? Why prove it again? I like points of view. I think this is a nice one. I want you all to have this point of view on how to think about this theorem. But this next one I think also really nice. So here it goes again. Let's assume that the matrix is diagonalizable. And let me just remind you what diagonalizable means. Different point of view. Up here, we talked about diagonalizability in terms of a conjugation. Now instead, I'm going to think about diagonalizability as a change of basis, namely preserving that linear transformation, doing a change of basis. I can represent that transformation in a different language, of course, as a diagonal matrix. Okay, that's equivalent to talking about a conjugation. This is just a different way of saying the same thing. Okay, so, recall diagonal matrices have easy eigenvalues and eigenvectors, and these are they. Right? We talked about that second page of the notes for this talk. This is a diagonal matrix. The standard basis vectors are the eigenvectors, and the diagonal entries are the eigenvalues. Right? And now I'm going to refer you back to an argument that we made that's very confusing, but it's a really valuable point of view to be able to take. That when you see a matrix equation, you can take that matrix equation, identify what language is being spoken in the assertion of this matrix equation, and then once you know what language, change the language. Just say it with respect to a different basis. Right? So that's what I'm going to do here. What language is being spoken in this conversation here? Well, D is clearly in the language of the script V basis. And given that, I realize that everything else in this equation must be in the language of this script V basis. So let's think in terms of this bunch of zeros with a 1 in the ith position. With respect to the script V basis that we're using here, with respect to that script V basis, what is that vector the coordinates of? And this is another one of these old sort of freebie. Every so often, everything lines up just perfectly. It's VI, because if you want to write VI as a linear combination of a list of vectors that includes VI, these are the coefficients you need. Right? Likewise, over here, same exact statement. Right? And so, having made this observation that this first matrix equation, easy observation about eigenvectors and eigenvalues of D, identifying the language is script V language, I can then say, and you know what? By the way, here's the other thing. Fooey on script V language. Script V language is arbitrary. I don't want to speak that language anymore. I just want to talk coordinate free. Right? So here, this is a statement about the linear transformations itself and the vectors themselves. And I can then say, hey, free country, I would like to say this now instead in standard basis language. And standard basis language for T scrolling back up, is A. And likewise, the way we think about vectors in Rn is that they are their own linear combinations of standard basis vectors in Rn. Likewise then here. So the nice punchline then is this statement about the matrix D tells us this statement about the matrix A. Again, ultimately, both of these two statements say the same thing. Both of these two matrix equations are really saying that. They're really telling you something about an underlying linear transformation, just in different languages. So the fact that we have free eigenvectors and eigenvalues of the diagonal form means that we have the ability to conclude eigenvectors and eigenvalues of the other form. Okay. All right, so that proves the result. Again, it shows that these vectors that were used to diagonalize, those are that is a basis of eigenvectors, and that's what we wanted to show. Okay, so it's a lot to digest. Take your time, right? Take the time as needed to digest these ideas about, well, for one thing, what is, how is a similarity the same as a change of basis? You got to roll that around in your head, right? Think about how that allows you to take a different point of view on diagonalizability. You can think of it as a conjugation, or you can think of it as a change of basis. Both points of view are important. Think about how eigenvectors make the diagonalizability work. First in this numerical example, then in this argument that takes sort of a conjugation point of view, and then in this argument that takes sort of a change of basis point of view. Lots to digest there. Okay, now I skipped a page that I now want to come back to. I put this page, this is not in the book at all. This is just something that used to bug me when I was learning this stuff coming up. And we talk about diagonalizing a matrix and other things that people say, or we talk about putting a matrix into diagonal form. You may recall long ago we talked about putting a matrix into reduced row echelon form, right? Both of these bits of terminology, there's something intrinsically uncomfortable about this. Wait a second, if you want me to take a thing that's defined, here it is, I want to talk about this matrix. I mean, if I put it into a form, wouldn't I be changing it, and then is it really still it? What does it mean how is it a meaningful statement that I'm going to take a matrix and put it into a form if it is no longer it? You know what I mean? So, for example, what if I were to come up with my own idea of a form? I'm going to call it the zero form. Right? And I'm going to put a matrix into zero form. And the way you put a matrix into zero form is you take your matrix, right? And then over here you just write down the zero matrix. There it is. I put this matrix into zero form. Well, that's meaningless nonsense, right? I mean, the zero matrix is not the original matrix, right? This doesn't have any information in it that's not in this, right? So, when we say we're putting a matrix into a form, but we're changing it, what gives? And the idea is that something's being preserved. So, yeah, sure, I'm putting a matrix into reduced row echelon form, but in that process, there is something that's not changing at all. And likewise, when I talk about putting a matrix into diagonal form, there's something that's being preserved, something that's not changing. And what's important to realize is that, again, the language does not give this away. But those things are different between these two processes. So here's a little table, compare and contrast between row reductions from chapter 1 and diagonalizations from here in chapter 5. When you put a matrix into reducer echelon form, well, there's reducer echelon form. That's the rules. That's the definition of reducer echelon form. The process by which you put a matrix into reducer echelon form. Row operations. Which, by the way, don't forget, row operations are just a shorthand for equation operations. Which, if you want to write them in matrix algebra, are elementary matrices. Right? So, you're allowed to do all of this you want to achieve this goal, and now the big question, and this all means what? What is it that's being preserved in this process? The set of solutions. Right, so you got to think way back to the very start of this project. Why were we row reducing in the first place? Because we wanted to solve a system of equations. We wanted to find that solution set. The big strategy, day one of this class, right, was we're going to find a solution set by coming up with things we can do that preserve that solution set, that don't change the solutions at all. And thereby we have a way of getting at what we're interested in by getting it into a form that makes life convenient. Okay. All right, so when we're doing row reductions, we're interested in the solution set. This process preserves the solution set, and we aim for this as our target because, well, it makes it easy to find the solution set, right? That was the big thing about reduced echelon form. It's easy to solve. Solve for your pivot variables in terms of your free variables and all that. Okay. Highly analogous, but with different details with diagonalization. What is a diagonal matrix? Well, it's easier to define a diagonal matrix. What's the process of diagonalizing? Well, we talked about this. It's similarities, conjugations, you might say, change of basis, something that takes a matrix and results in another matrix that's similar to it. And why? Right? What is it about these things here? What does this preserve when you do a conjugation? But even more to the point, what is preserved when you do a change of basis? Well, the underlying linear transformation. So said differently, because we're interested in understanding an underlying linear transformation, we can do this till the cows come home because it preserves that underlying linear transformation. And we can just conjugate all you want, keep conjugating. Now, don't we eventually want that process to kind of terminate, right? I mean, what is the easiest way to understand a linear transformation? Well, it's going to be hard to beat diagonal form. If you have a matrix, a diagonal matrix representing a linear transformation, that makes it pretty easy to understand that linear transformation. Okay, so anyway, this is the big idea here. I want to supplement this table here a little bit. This is what we call similarity. Right, change of basis and conjugation both result in similar matrices. Along those lines, this is what we call row equivalence, or sometimes we just call it equivalence. Both of these, the notion of equivalence, the notion of similarity, I've already talked about the semantics a little bit. Let me just say it one more time. Both of these terms, equivalence and similarity, suggest something underlying that the two matrices have in common. With equivalence, the two matrices have the same underlying solution set. With similarity, they have the same underlying linear transformation. Okay, so there's a strong analogy between similarity arguments and equivalence arguments, between diagonalization and row reductions. there's, like I say, a structural kind of analogy there, but everything's different. The goal is different. The means are different. What's being preserved is different. Make sure to keep that in mind, right? So the tragedy that happens from time to time is that a student wants to diagonalize a matrix. Wants to diagonalize a matrix to understand a linear transformation, and then they do so by doing row operations. That doesn't make any sense at all, right? So that this is absolutely inappropriate, sort of catastrophic. Don't do that. You got to identify, what is it that you're trying to understand, and that dictates what you're allowed to do and where you should be aiming. Okay. All right. Now let me just go a little further. Let's see here. Just as a kind of a summary of what we've talked about today, this will be a nice sort of cap for the lecture. Diagonalization looks like this. Diagonalization means a conjugation resulting in a diagonal matrix. A little bit of matrix algebra shows that that's equivalent to this. Not only is D a conjugate of A, well, also A is a conjugate of D. Like I say, easy algebra there. Again, you can think about it in terms of conjugates, or alternatively, you can think about it that this conjugating matrix is a change of basis matrix. And what we showed with those theorems is that the columns of that change of basis matrix are a basis consisting entirely of eigenvectors. Okay, so this is several things that are always consistent with diagonalizability. If a matrix is diagonalizable, then that's true, and this is your P matrix, and that's your change of basis matrix. And then likewise, if a matrix is not diagonalizable, then that's not true, and that's not true, and there is no such matrix, and there is no such basis. So it's a nice sort of paralleling little summary there. And then a very quick last comment. Students look at these two equations, and sometimes, they look kind of alike. It's really easy to inadvertently get the inverse in the wrong spot. Like, how do you remember that the inverse kind of goes on the left over there, and it kind of goes on the right over there? So aside from the fact that sometimes you'll just misremember. So I like to point out that you don't need to remember. I personally don't remember. I'm real bad at remembering details. Right? So what I want to encourage y'all to do is don't memorize your way through that question. Think about what stuff means and then draw your conclusions as needed. So, for example, suppose you've decided that you need to know A as some sort of a conjugate of D, but oh gosh, which way does it go? Which one's the P inverse and which one's the P? Could be very confusing. Just remember that, well, let's suppose A is standard basis language, and let's suppose that D is script V language. Well, then this equation that we're looking at here really means this. And looking at it from this point of view, it's perfectly obvious what goes where. The language of the input to that matrix has to be the same as the language of the output from that matrix. And the language of the output from this has to be the language of the input from there. So I instantly know that this has to be script V, and that has to be script V. And likewise, the language that comes out there, well, that has to match with the language that comes out there, and the language that goes in here has to be the language that goes in there. And so it has to be that that's standard basis and that that's standard basis. And that resolves the matter for you. You don't have to memorize anything. This matrix here is the P matrix. If that's the one that you've chosen to call P. If, the one whose columns are the eigenvectors, well, that's the V to S matrix. And therefore, the inverse goes there. Okay, all right, good stopping point. See y'all later. Have a good Wednesday.